Hi everyone, am I audible? Okay, so now we will start some recurrence relation related problems. Okay, how to write recurrence relation for some questions for some combinatorics problems. Okay, so anyone has any doubts so far? Before we start, anyone has any doubts so far? Okay, so let's start. So first, you can notice this is a GATE 2014 question, and actually regarding this recurrence relation on Go Classes YouTube channel, you can find a playlist. In that playlist, I think almost 7 or 8 questions are there for which I have written the recurrence relation. How to write the recurrence relation for combinatorics problem? Okay, so that I have already discussed in that playlist. Okay, so maybe some of you have already watched that playlist. So for those students, this question will be very easy. Okay, so basically you have a combinatorial problem. Okay, so you have a counting problem, I can say. Okay, so you have a counting problem, and for that counting problem, sometimes what we can do, sometimes we can write recurrence relation. Okay, so sometimes this is what we can do, we can write recurrence relation for a counting problem. Okay, so once we write the recurrence relation, then we can solve this recurrence relation and we can get the answer. Okay, then we can basically solve it. Okay, so now writing the recurrence relation itself is very interesting. Okay, so that is the reason many questions in the GATE exam are based on writing the recurrence relation. So basically there is a counting problem, and from that counting problem, how to write the recurrence relation. Okay, solving the recurrence relation is not a big thing. Okay, because actually in the GATE exam also, if you notice, then very rare, like I think only one question is there where recurrence relation is given and they are asking you to solve the recurrence relation. Okay, but writing the recurrence relation is very important. Okay, many questions are there in the GATE exam on this topic. Okay, so before we see this, let's see how to write the recurrence relation. Okay, for example, consider this. Okay, so this example is already present in that playlist. As I told you, Go Classes YouTube channel, you can find a playlist recurrence relation. Okay, in that playlist already this example is there. Okay, so let's see, find a recurrence relation and give initial conditions for the number of bit strings of length n that do not have consecutive zeros. So for this, how to write the recurrence relation? Are you getting this point? So number of bit strings of length n that do not have consecutive zeros. So how can we write recurrence relation? Writing the recurrence relation is very simple for this. So let us assume what is an. So an means, let's assume number of bit strings of length n. Okay, so let's assume. So let me write this. So assume that an means number of bit strings of length n without consecutive zeros. Okay, without consecutive zeros. Now if this is your an, then can I write this an in terms of an minus 1, an minus 2, etc. Basically our task, what is our task? Our task is to remember, this is recurrence relation. Recurrence relation means basically our task is to write this an in terms of an minus 1, an minus 2, and so on. Okay, so this is our task, to write this an in terms of an minus 1, an minus 2. Can anyone tell me what is an minus 1? Can anyone tell me what is an minus 1? So from this you can notice an minus 1 means length n minus 1. Yes or no? Number of bit strings of length. So this is basically number of bit strings of length n minus 1. Of length n minus 1 without consecutive zeros. Without consecutive zeros. Okay, so now you can very easily write. So finally, what you can say, now here what you can do. So first you notice that this is your bit string of length n. Okay, so this is length n. Now focus on any one position. For example, focus on this position. Focus on this position, this ending position. Okay, Now you can notice there are two cases. Either this can be 0 or this can be 1. Yes or no? So either this case can be 0 or this can be 1. Okay, so either you can put 0 here or you can put 1 here. Now notice that if this is 0, then if this is 0, then what will happen? Then how many bit strings I have? Just tell me this point. If this is 0, then how many bit strings I have without consecutive zeros? See, if this is 0, then you can notice this cannot be 0. This has to be 1. Yes or no? Because we should not have consecutive zeros. So notice that if this is 0, then this cannot be 0. This cannot be 0. This has to be 1. Okay, this has to be 1. If the last position is 0, then this has to be 1. Now you can notice, now here we should not have consecutive 0. Yes or no? So basically now I can say that here I should not have consecutive 0. So I can say I will count an minus 2. I will find what is an minus 2. I will find this an minus 2. Okay, because here now I will, okay, here I should not have consecutive zeros. So I will find an minus 2. And you can notice, so this is your case 1 where the last position is 0. And what is case 2? What is case 2? When the last is 1, now you can notice, now here I should not have consecutive 0. So now I will find what is an minus 1. Okay, yes or no? Here I will find what is an minus 1. So finally, either case 1 is possible or case 2 is possible. Yes or no? Only two cases are possible. Okay, so our main task is an. For that an, only two cases are possible. Either this case is possible or this case is possible. In this case, our answer is basically here we have to count an minus 2 because automatically this will be 1. And here we have to count an minus 1. So either this is possible or this is possible. Are they mutually exclusive? Can I say they are disjoint? Can I say this case and this case, are they disjoint? Do they have anything in common? No, they are completely disjoint because here the last position is 0 and here the last position is 1. So finally I can say that an is equal to an minus 2 plus an minus 1. Okay, so this is the recurrence relation. What is the initial condition? Can anyone tell me what is the initial condition? So an is equal to an minus 2. Okay, if you want to find for n length bit string, you can find for n minus 2 length bit string. You can find for n minus length. Okay, so this is, and what are the initial conditions? We need two initial conditions actually. Here here we need two initial conditions because for example, if I give you one initial condition, just think about it. Just think about it. If I give you A1, can you find A2? From A1, can you find A2? If I give you one initial condition, can you find A2? You cannot find, because if you want an, then you need this, you need this. So you need two initial conditions you need. Okay. So what is A1? A1 is simply 2. Correct? Because A1 means, okay, what is A1? A1 is basically, okay, I can say 0, 1. Okay, this is your A1. And what is A2? A2 is 3. Okay, because what is A2? A2 is simply, okay, so 0, 1, 1, 0, 1, 1. This is A2. So A1 is 2, A2 is 3. Now, very simply, from this recurrence relation, you can find A3. What is A3? From this, you can see that A3 is A2 plus A1. So A3 will be 5. What is A4? A4 will be A3 plus A2. So that will be 5 plus 3. So that will be 8, like this. So this is how you can write the recurrence relation for combinatorial problem. Is this clear to everyone? How to write recurrence relation? If you want more questions for practice, then you can just, okay, on Go Classes YouTube channel, you can find this playlist. Okay, Go Classes for Gate CS, for Gate CS. Okay, so this is the YouTube channel. Okay, this is the YouTube channel. And on this YouTube channel, you can find a playlist. Okay, so there is a recurrence relation playlist. Okay, so that is recurrence relation. So in this playlist, you can practice. Okay, I think total many examples are there. Okay, so you can just practice all these questions. Anyway, this is the idea. Okay, so let's see one more question. Can you try? Can you try this question? Question number 13. Can you try this? Anyone? A string that contains only zeros, ones, twos is called a ternary string. Find a recurrence relation for number of ternary string of length n that do not contain two consecutive zeros. Yes, it is free. Revision course is free for all. Okay. So can you try question number 13? Can you write the recurrence relation for this problem? Ternary string containing do not contain consecutive zeros. Ternary string that do not contain consecutive zeros. So what is the recurrence relation for this question number 13? Try this. So for question number 13, this is okay. So very simple. So first of all, you have ternary string. Okay. So again, you can notice what is an. An is basically number of ternary strings. Okay, this is basically number of ternary strings. Number of ternary strings not containing consecutive zeros. Not containing consecutive zeros, not containing consecutive zeros. So here you can notice, again you can notice very simple. So how to find this an? Basically our task, okay, remember our task is what? Our task is to find this an in terms of, okay, in terms of an minus 1, an minus 2 and so on. Okay, an minus 2 and so on. So here you can notice that again there are two cases possible. Okay, so what are the two cases possible? Either the last is 0. Okay, if the last is 0, or the last is either 1 or 2. Okay, so either this is 1 or 2. You can notice either this is 1 or this is 2. Okay, if this is 1 or 2, then what should we do? Then we have to count an minus 1. Yes or no? Okay, now we have to find an minus 2, an minus 1, because here we should not have consecutive 0. Okay, in this portion, in this area, we should not have consecutive 0. In this area, we should not have that. Okay, so if this is 1 or this is 2, then we should have an minus 1. Okay, here. If we have 0, then what should I do? If I have 0, then definitely here you either you should have 1 or you should have. Yes or no? If this is 0, then definitely you must have 1 or 2. Then I will count an minus 2. So finally, what can I say? Tell me. Finally, I can say that you want this an, then there are two cases possible. Okay, either the last is 0 or the last is 1 or 2. Either the last is 0 or the last is 1 or the last is 2. Okay, or the last is 2. Okay, so here you want an minus 1. And here you want what? Because here automatically this will be 1 or 2. So here you want an minus 2. So finally, I can say an is equal to what? That is twice an minus 1, because here you have two choices. Remember, here you have two choices. So I can say this is twice an minus 1 plus. Here also you have two choices, either 1 or 2. Then again you have twice an minus 2. Okay. So this is your recurrence relation. How many of you got it? Okay. Yes. Sandeep, correct. Anari, correct. Not correct, actually, an minus 2. 2an minus 1 plus 2an minus 2. Okay, this is how you can write. What are the initial conditions? Can anyone tell me what are the initial conditions? Anyone? So the initial conditions. Initial conditions are very simple. What is A1? A1 is 3. Because what is A1? A1 is basically, A1 is 3. Okay, so you can just check. This is 3. 0, 1, 2. Okay, so this is 3. And what is A2? A2. Okay, A2 is basically, I can say, here you can have, for example, you can have, instead of 0, 0, you can have everything basically. Okay, you can have, instead of 0, 0, you cannot have 0, 0. Everything else you can have. Okay, you cannot have 0, 0. Okay, so apart from 0, 0, you can have anything. For example, you have three choices, here three choices. Okay, so total, you have total, okay, 3 into 3, that is, okay, 9. 9 minus 1. This minus 1 is due to 0, 0. Okay, so total 8. So A1 is 3. Okay, yes. And you can notice, so because three choices, so minus 1. Okay, this will be 8. So finally, you have, now you can find A3. What will be A3? This is the recurrence relation. So that will be twice of 8 plus 3, that is 11. So that will be 22. Okay, so A3 will be 22. Like this, you can find A4. Okay, so what will be A4? A4 will be twice of 22 plus 8. Okay, so that will be 60 and so on. Okay, like this you can find. Is this clear? Is this clear to everyone? Okay, so like this. And can you tell me what is the answer for 14? What is the answer for 14? Find a recurrence relation for number of ternary string that contain consecutive zero. They should contain consecutive zero. Containing consecutive zero. Tell me, can you try? Number of ternary string containing consecutive zero. No, we have to write recurrence relation. Okay, I am not asking answer. I am not asking answer. I am asking writing the recurrence relation. Can you write the recurrence relation for this problem? Okay, like can you find an? What is an? An is basically number of n length ternary strings. Number of n length ternary strings. Ternary strings that do not contain consecutive zero. That do not contain consecutive zero. In GATE exam, many times they are asking, they will give you some statement and they will ask you what is the recurrence relation. Okay, so there are many questions based on this topic. Okay, you can find it in the Go PDF. You can find these questions which are based on recurrence relation. You should know how to write the recurrence relation. Okay, because sometimes options will not be given. They will not give you options. Okay, for example, okay, in some questions they will not give you option. In this question, for example, here they will not give you option. They will ask you what is A6. They will ask you what is A6. So they will not give you option. Okay, so sometimes, so anyway, you should know how to write the recurrence relation for problems. So can anyone tell me how to write this? Anyone tried it? Try this. If anyone want to practice these things, then you can just go to the YouTube channel of Go classes and there is a playlist, recurrence relation. In this playlist, you can practice. Okay, there is already a playlist. Find this playlist and practice. Okay, let's come back to this question. So what is the answer now? It must have consecutive zero. We must have consecutive zero. Our focus should be on having consecutive zero. Okay, so let me try. Okay, so the question is very simple. First of all, okay, if the last bit is zero, then what should happen? Okay, see, if the last bit is zero, okay, first let me see the simple thing. If the last is either one or two, then what should I do? Then what should I calculate? Just tell me this point. Okay, if the last bit is one or two, then what should I do? Then I should find consecutive zero here. Then find consecutive zero here. Then find consecutive zero here. Okay. If last is either one or two, last position is either one or two. If the last position is one or two, then I should find consecutive zero here. Correct? Is this clear? Okay. So, but if last is zero, then what should I do? If last is zero, if last is zero, if last is zero. Now there are again multiple cases. Again there are cases. What are the cases? If last is zero, if last is zero and this is also zero, then what should I do? My task is over. Can you notice? Can you notice my work is done? My work is done. Now anything can be here. Now here anything can be. Now we can have anything here. Now we can have anything, means 2 power n minus 2 possibilities. Now we can have, sorry, 3 power n minus 2 possibilities. Anything we can have here. Here you must find consecutive zero. Okay, if the last is zero, and this is either 1 or 2, then what should I do? Then I should find consecutive zero here. Then I should find an minus 2. Yes or no? Because now I should find consecutive zero here. Yes or no? So these are the points. Okay, here an minus 1 plus this and this. So finally I can say that an that is equal to here two choices. Okay, because here we have two choices. So 2 an minus 1. So that is 2 an minus 1 plus, okay, plus here 3 here. Okay, you can check it out. So here again 2 an minus 2 2an minus 2 plus 3 power n minus 2. This is the recurrence relation. To how many people this is clear? Many students have given correct answer. So is this clear? Can you write recurrence relation for the combinatorics problems? Okay, yes or no? You can write the initial conditions also. Okay, so you can try the initial conditions. Initial conditions are very simple. What is a2? Can you tell me what is a2? A2 will be 1 because consecutive 0 must be there. Okay, A2 will be 1. And you can find what is A3. Consecutive 0 must be there actually. So A1 will be 0. You can find A3 also. Okay, so from this also you can find A3. A3 will be here. You can just check it out. Okay, so A3 will be actually, you must have consecutive 0. So maybe 0, 0, okay, 1, 0, 0, 2, or maybe 0, 0, 0, 0, 0. Okay, or maybe 1, 0, 0 or 2, 0, 0. So actually answer this A3 must be 5. This must be 5. Can you check? So is it coming? Is it coming 5? Is this coming 5? We are writing recurrence relation. Soumya, we are writing recurrence relation. We are not finding the answer. We are not finding any answer here. We are writing the recurrence relation. Basically, we are writing an. Our task is this. This is our task. Our task is to write this an in terms of the previous terms. This is our task. Okay, this is our task. Our task is to write an in terms of previous. Okay, so can you tell me? Okay, so here you can notice A3 is 2an minus 1, which is A2. Okay, plus 2, 0, plus 3 power 1. Okay, so you can notice this is also 5. So you can find A3, that is 5, and so on. You can find A4, A5. Okay, so you can find A4, you can find A5, and so on. So basically, this is recurrence relation for this sequence. Actually, I can say that for this sequence, okay, for this sequence, so you have A1, which is 0, okay, and you have A2, which is 1. Now you have A3, which is 5, and similarly you can have, okay, and so on. So similarly, so for this sequence, the recurrence relation, okay, for this sequence, this is your sequence, I can say. Okay, so for this sequence, the recurrence relation we have, for this sequence we have recurrence relation. And what is that? The recurrence relation is basically, okay, an is equal to 2an minus 1 plus 2an minus 2 plus 2 plus 3 power n minus 2. All possibilities are considered. Sandeep, here all the possibilities are considered. See, notice that all the possibilities are considered. Notice all the possibilities are considered. Can you check? Every possibility is also already considered. If you check it, it does not matter. You don't have to start from end. You can start from the beginning. You can start from the middle. See, you can start from the middle. There is no, you can start from the beginning. You can make cases like this. You can make cases like this. Okay, then here you have again an minus 1, and here again you have two cases, 0, 0, now 3 power n minus 2, 0, 1 or 2, then this is an minus 2. Isn't it clear? Tell me. So you can start, okay, like there is no restriction. There is no restriction. You can do like this also. And all the possibilities are considered. Okay, so like this you can write the recurrence relation. Can anyone write the recurrence relation for this problem? Okay, you can try this. I will share these slides. I will share. Okay, so the question is here. This is the question, and this is the answer. Okay, so you can check the answer also. Okay, so this is the initial condition, and this is the, so answer is also available. So I'm giving this as a homework. Okay, take this as a homework. You take. Okay, so the answer is already available. You don't have to worry. Okay. Now let me go and check this GATE question. Okay, let's solve this GATE exam question. Okay, so try this GATE 2014 question. Can anyone try GATE 2014? Is it done? So you can notice the question is very simple. So he is saying that a pennant, okay, a pennant is a sequence of numbers, each number being 1 or 2. N pennant is sequence of numbers with summation of n. For example, 112 is 4 pennant, and you can notice that this, okay, so this is 3 pennant. 1 to 2 1 are different. The number of 10 pennants. So the question is basically very simple. If you write the recurrence relation, you actually see, just by reading the question you can understand that, okay, you should try to write the recurrence relation. Just by reading the question you can see that you should definitely try to write the recurrence relation. Okay, so what you should do, very simple. So here you can notice that the question is asking the number of 10 pennants. Let's find out number of n pennants. Okay, so what is the number of n pennants? So you can notice here, okay, so let me find out number of n pennants. So you can notice that what is a pennant. First of all, you understand that. So what is a pennant? Pennant is basically a sequence of numbers where 1 or 2. Okay, for example, this is a 4 pennant. Okay, for example, this is a 2 pennant, this is a 2 pennant, 1 or 2. So for example, can anyone tell me what is this? How much pennant is this? This is how much pennant? This is a, you can notice this is 2 to 4 and 4 4 8. This is 8 pennant. You can notice this and this are different. This and this both are different actually. So for example, this and this, if I do 1 to 1 1 to 1, these are different. Okay, so anyway, the point is this is 8 pennant, and similarly this is also 8 pennant. 1 1 1 1 1 1 1 1. This is also 8 pennant, this is also 8 pennant. Okay, like this. So you can very easily notice that finally I can say that if I want number of n pennants, let's call it an. Okay, now you can notice, just think about it and tell me the first pennant, either that can be 1 or that can be 0. Yes or no? So either that can be 1 or that can be 2. The first pennant, either that can be 1 or the first pennant can be 2. Correct? If the first pennant is 1, then how much I need? I want an minus 1. If the first pennant is 1. Okay, if the first number is a 2, if the first number is 2, if the here first number is 1, then I want an minus 1. If the first number is 2, then I want an minus 2. And all the possibilities are covered. So finally I can say that an is equal to an minus 1 plus an minus 2. And what are the initial conditions? Can anyone tell me? Initial conditions are already given to you. So an is equal to an minus 1 plus an minus 2. Anyone remembers this popular, is this recurrence relation is familiar to you? Are you familiar with this recurrence relation? This is a popular recurrence, Fibonacci. Yes or no? So this is a Fibonacci recurrence relation. Okay, anyway. So what are the initial conditions? So here the initial conditions, you can find it out. So for example, 1 pennant, the set of all possible 1 pennant is already given to you, and the set of all possible 2 pennant is also given to you. Okay, and the set of 3 possible pennant is also given to you. So I can say possible 1 pennant. Okay, so that is also given to you. A2 is also given to you. Okay, and A3 is also given to you. So you can just check it out. So these are already given to you, and now you can very easily find the A10. The question is asking what is A10. Okay, so from here you can very easily, so you just got a sequence, right? So it's like A1, A2, A3, A4, A5 and so on. You got a sequence. So it's like 1 2 3, and every term is previous 2 terms, summation of previous 2 terms. So this will be 5, this will be 8, this will be 13, and then 13 and 8, that is okay. So like this you can find. Okay, so similarly you can just, okay, you can just find the okay, you can just find the A10. Okay, like this you can go. Okay, so A1, A2, A3, A4, A1, A2, A3, A4, A5, A6, A7. So this is A7. And what is A8? So you can just add them, and okay, so this is A8, right? Okay, 1 2 3 4 5 6 7, and this is 8. So that will be, sorry, that is 34. Sorry. So that is 34. Okay, and then you have 5 and 5, and then this is A9, and finally you can add these two, and then you will get 9 and 8. and this is your 8, 10. So you can notice in the GATE exam, they are asking 10 penance. Okay, so the answer will be 89, and this is how you can find. Okay, so this will be the answer. Anyway, okay. In this question, can anyone tell me, like if I make a variation, I want to create one variation. How many 10, for example, how many 20 penance you have where only two numbers are allowed? For example, this is a sequence of numbers, right? So how many 20 penance of only two numbers? So let me create a variation. Can anyone try this variation? Basically, how many 20 penance? How many 20 penance? Okay, containing only two numbers. Containing only two. Sorry, no. Actually, because every number 20 penance is not possible. Okay, sorry. Actually, this variation is actually not possible. Okay, yeah, I will create some different way. Okay, actually this variation is not possible because every number is either 1 or 2, so this is not possible. Okay, so this is yeah, this is not possible. Okay, anyway, let's come back to, okay, so can anyone try? Okay, quickly tell me the answer for this question. Find the recurrence relation for number of ways to climb n stairs. If one person can climb the stair, can take 1 or 2 stairs. Can you notice this is the same previous problem? This problem is same as the previous problem. Same, yes or no? So here the answer will be actually, okay, so Sn, that will be basically Sn minus 1 plus Sn minus 2. And what is the initial condition? The initial condition. Okay, so for example, if you have one stair, then only one. If you have two stair, then two. If you have two stair, then two. Okay, so again, you can notice this is a this is the same problem. This is the same previous problem, exactly same. There is no change. In the previous problem, also the same initial conditions we have. Okay, so like this. So anyway, these are some questions based on recurrence relation, how to write the recurrence relation. Is this topic over? Tell me. Like, is this topic clear to you? Tell me. We have taken some questions, enough questions I think we have taken. If anyone want more questions, then you can check out the playlist, the recurrence relation playlist you can check out on the Go Classes YouTube channel. Okay, 8 more questions are already available there, so you can try 8 more questions. Okay, so anyway, in the GATE exam already some, I think 4 or 5 questions have been asked on this topic. One last question we will take is derangement recurrence relation. You know what is the derangement problem, right? Yes or no? So this derangement problem, what is this? Can anyone tell me what is the derangement problem? This is a popular problem, you can notice. So what is the derangement problem? The derangement problem is basically like this. Okay, basically no one is at its own, no one in his home. Okay, so basically I can say no one in its own home. Okay, so this type of situation is basically derangement. So this situation is known as derangement. Okay, so it's like, for example, let us assume that this is the house of A. It's okay, you already know, but let me tell you. For example, let us assume this is the house of A, this is the house of B, this is the house of C. So here A lives, here B lives, okay, here C lives. Now one day what happens is that, okay, so you, okay, notice that these two situations you notice. So these are the houses. This is the house of A, house of B, house of C. Okay, or let me call it house number A, house number 1, 2, 3. Let me call it like this. So you can notice number 1, 2, 3. So this is house number 1, 2, 3, and this is house number 1, 2, 3. Now one day what happens is that B is here, okay, C is here, A is here. Okay, for example, B is here and A is here, C is here. Which of these is derangement? Tell me, which of these is derangement? So you can notice this is derangement. Okay, so first of all, because no one in its place, so this situation is known as derangement. Derangement. Here you can notice C in its own home. Okay, so this is not a derangement because C is available. C is present in his own home. So this is not a derangement problem. Not derangement. Okay, so this is not a derangement. Why? Because C in its home. Okay, so C is already in its home. So this is anyway. So this is your derangement problem, means no one in its own place. Okay, now if you have, let us assume n home, then okay, how many derangements are possible? For example, if you have, okay, 2 people, okay, with 2 elements, how many derangements are possible? If you have two elements, see one element, with one element, how many derangement are possible? Tell me. With one element, then tell me with the two element. With one element, derangement is not possible. So zero derangement possible. With the two element, one derangement possible. Okay, it's like this. With one element, this is the derangement that is possible. Okay. With three element, what is the derangement possible? With three element, you can notice that, okay, if two is here, if two is here, then the only possibility is 3, 1. This is the only possibility. And if two is here, if 2 is here, then the only possibility is this. So, okay, the three element derangement. Okay, so that is three element derangement. So I can say with one element 0, with the two element this is 1, and with the three element this is a 2. And similarly, you can find for 4 elements and 5 elements and so on. Okay, you can find. So what is D4? What is D4? You can check it out. Okay, we will write the recurrence relation and then we will find. Okay. So what this is what we are going to do. For example, what is D8? Okay. So like this. Okay. So if I ask you what is D8, then basically we want a recurrence relation. Yes or no? So let me write a recurrence relation first. So first what we are going to do is, okay, so write the recurrence relation for Dn. So this is the question. Okay. So can you write the recurrence relation for Dn? Okay, so basically Dn you already know. Dn means n elements. Okay, so basically our task, what is our task? Our task is to write this Dn in terms of Dn minus 1, Dn minus 2, and so on. Okay, so this is our task. Okay, so how to proceed? Actually, this is very easy if you apply the same idea that we have seen. Just apply that same idea. Basically, take one person and just basically analyze around that person. Are you getting my point? Take one person and analyze around that one person. For example, let us assume these are the homes. Okay, let us assume these are the homes like this. Total, okay, home number 1, home number 2, and so on. Now, these are the homes. Okay, take one person, any one person. For example, let me take this person number n. Okay, let me take this person number n. So let's assume, okay, tell me, I want derangement. Then it means, what are the possibilities? How many possibilities for n? Can anyone tell me? I want derangement. So how many possibilities for n? N minus 1. Yes or no? Or I can say that these are A1, A2, A3, An. So how many possibilities for n? An minus, I want derangement. We want derangement. So you can notice we want derangement. Okay, so here we have, okay, total n minus 1 choices for n. Okay, choices for an. Focus, okay, just work around, okay, analyze around an. Now we will do our analysis, okay, around this an. Okay, so this is your an, and we are basically just going to an and we are asking him, okay, what is the problem? Okay, so now you can notice these are n minus 1 choices. Now you can notice there are two cases. Okay, can you notice? Okay, this an will go to someone else's houses, someone else's house. For example, this an is going to, let us assume this an is going to this house. Okay, means an is going to basically P's house. This an is going to P's house. This is n's house. This is 1's house. This is 2's house, and so on. Now you can notice this an, this is going to what? Can you notice? This an is going to P's house. So basically I can say, assume an is going to P's house. Assume an is going to P's house. Okay. Now there are two cases possible. Can anyone tell me what are the two cases possible? An is going to P's house. Then what are the two cases possible? Here actually two cases are possible. Can anyone see that? Just try. Just try this. You, okay, step by step I am going. See, nothing big I am doing. Okay, very step by step I am going, because you can notice that, okay, take one person. In the recurrence relation, this is what we do. Yes or no? Most of the time in recurrence relation, we take one person, we take one position, and we work around them. Yes or no? This is what we have seen. Yes or no? This is general trend. Generally, while writing recurrence relation, what we do? What happens while writing recurrence relation, we work around some one or two position. Yes or no? We work around few specific positions, and do complete analysis. Okay, so anyway, here I am taking this an and I am working around an. Okay, so analyze around an. Let me analyze around. Okay, you can analyze around anyone. Okay, let me analyze around an. Okay, so let us assume an is going, an has n minus 1 choices. Let us assume an has going to P's house. Now there are two cases possible. What are the two cases? Yes, so basically, of course, P has to go to someone's house. Now there are two cases actually. Okay, the case one, P goes to N's house. Yes or no? P goes to N's house. See, N is going to P's house. So N is going to P's house. So P goes to N's house. Yes or no? So AP goes to N's house. Either this is possible. What is another case possible? Tell me. What is another case possible? AP goes to, AP does not go to AN house. Yes or no? Either this is possible. AP does not go to AN's house. Yes or no? Now tell me, if AP goes to AN's house, then what should I then what should be the answer? If AP goes to AN's house, see, AN is going to AP's house and P is going to N's house. So how many? AN minus 2. Very good, excellent. Because if AP is going to AN's house, then I need to count AN minus 2. This is what I need to count. AN minus 2. This is what I need to count. If AP is going to AN's house. What is another situation? AP does not go to AN's house. It means what? Okay, AP does not go, AP does not go. It is like, yes, very good, very good. It is like this, something like this. Just think about it. It is like this. Now, this situation, how can you think this situation? It's like this, that just think that AP is derangement with respect to what? Can you notice? AP is derangement with respect to, because AN is already in the P's house. Now, AP cannot go to AN's house. It means AP is derangement with respect to AN. So total AN minus 1 we need. Yes or no? In this situation, we need AN minus 1. To how many people this is clear? Just tell me. Is this clear to everyone? What I am saying? See, this case is very simple. That AP is going to AN's house. So this case is very simple because AN is going to, it's like, okay, case 1 is like this. Case 1 is like this, that this is N's house and this is P's house. Case 1 is very simple. AN is here, AP is here. So the remaining people will derange. So the basically, so remaining people will derange. So remaining, I can say, so remaining N minus 2 people will derange. Okay, because these will derange, because these are already deranging. These are already deranged. Okay, so the remaining people will derange. And in case 2, what is happening? In case 2, what is happening? In case 2, I am saying that it's like, okay, forget about AN. Okay, it's like this. In this situation, A1 is there, A2 is there, and it's like that. Just give it home. Okay, this is the house of A1, and give it home. For example, 1, 2. Okay, here you have A1, here you have A2, and here in this house, in N's house, you have AP. So now derange them. And but one position is gone. But one position, okay, just forget about one position. This position you, okay, don't consider, because here AN is sitting. Okay, so what I am saying is derange these things you derange. Okay, so these things you derange. Okay, if you derange these things, then you can notice that AP cannot go to N's house. You can notice this AP cannot go to AN's house if you derange all of them. Then finally I can say AN, case 2 means AN minus 1. So final answer is what? Tell me, what is the final answer? So dn is equal to, I can say, or I can say, okay. So what is derangement of n elements? That is equal to derangement of n minus 1 element or derangement of n minus 2 element multiplied by n minus 1. From where this n minus 1 is coming? Can anyone tell me? These are the choices for n. Yes or no? These are the choices for an. Okay, I hope this is clear. So this is our last example of recurrence relation. I hope this is clear. Like, are you finding this recurrence relation interesting? This is an interesting topic actually, writing the recurrence relation. This is quite interesting topic. This is how you can write the recurrence relation for derangement. Anyone got it? Did you find it little bit interesting? I hope, like, when I once studied this, okay, like maybe 3 or 4 years ago, when I studied this recurrence relation, I found it very interesting. And from that time, you can notice writing recurrence relation is my favorite. Okay, because this is very interesting thing. So anyway, I hope this is clear to you. So basically, these are the choices for an. Okay, n minus 1. These are the choices for an. Now, once you pick a particular choice, once you pick a particular house, means P's house, then these are the choices. dn minus 1 plus dn minus 2. This is your recurrence relation for derangement. So finally, anyone ask you derangement recurrence relation? So this is that. So derangement recurrence relation. Okay, so you can very easily understand that this is the derangement recurrence relation. Okay, and what are the basic conditions? Can anyone tell me what are the basic conditions? D1 is 0, D2 is 1, and you can notice from here you can calculate D3. What will be D3? D3 will be 3 minus 1. So you from here you can calculate now. D3 will be 3 minus 1, and this plus this 0 plus 1. Okay, so that will be 2. So now you can calculate D4. What will be D4? D4 will be 3 multiplied by 2 plus 1. Okay, so that is basically 9. D4 is 9. Yes or no? Choices of an is n minus 1, not clear to you. See, this is a very simple point. You can notice. See, an should derange. Then how many choices an has? Just think about it. You should not be present in your home. Then how many choices you have? You can be present in any of these home. So n minus 1 choices an has, right? N minus 1 choices an has. Because an is not present in an's home. We want derangement. Okay, we want derangement. So an cannot be here. An cannot be here. An cannot be here. So for an, we have n minus 1 choices. An can be here. An can be here. Yes or no? Is this clear? Okay. So this is the last example for writing recurrence relation. Okay. So this is how you can write the recurrence relation. And now you can calculate. If anyone asks you whatever they ask you, for example, now can you calculate what is D5? What is D5? Can anyone tell me? What is D5? From here you can calculate 4 into 9 plus 2. So that is 44. D5, 4 into 9 plus. So from this you can very easily find now. Okay. I hope you will never forget it. See, once you remember the logic, once you understand the logic, now you will never forget it. If you forget it, you can just quickly derive it. Notice that an has, okay, these are the choices for an. So I can just give you summary. Okay, let me give you summary. So summary, or let me give you summary here. So for example, summary is like this. From where this dn minus 2 is coming. So these are the choices for an. So let me write it. So first of all, these are the choices for an. These are the choices for an. And what is this? What is this? This means AP not in an's house. Yes or no? And this means AP in an's house. That's it. Yes or no? So this is the final summary. Okay, this is how you can remember. Okay. Okay. Can we solve every counting problem by recurrence relation? When should we go for recurrence relation? No, you cannot solve. See, combinatorics is a field of tools. Let me tell you, this combinatorics is nothing but a field of tools. In combinatorics you have tools, and we use these tools to solve problems. Many tools you have. For example, you have some rule. Sometimes you can use some rule. Can you always use some rule? Can you always use some rule? No. There is something called product rule. This is a tool. Can you always use product rule? No. There is something called generating functions. This is a tool. There is something called recurrence relation. This is a tool. There is something called inclusion exclusion principle. This is a tool. All these things are tools. Okay. Now just tell me this point. One more point I want to ask. In your home you have tools. Okay. There is a toolbox in your home. Okay, in this toolbox you have many things. Okay, for example, maybe okay, in this toolbox you have knife, and you have maybe a screwdriver. Okay, so many things you have, and so on. Okay, so can anyone tell me, how did you know when to use knife and when to use screwdriver? Can anyone tell me, how do you know when to use this, when to use that? It comes by practice. It comes by experience. It comes by practice. Yes or no? Similarly, this combinatorics is nothing but a set of tools. Many tools we have. Time to time new tools are being, okay, for example, this generative function is not on, this generative function is new. This is not old. These things are very old. These things are very old principles. These are very old laws, but generative function is quite new. So you can notice new tools are coming. Okay, there are many more tools. When you go to MTech, ISC, okay, in ISC, IIT, if you do MTech, there are many more tools you will study. Now, which tool to apply in which problem, that will come by practice. Okay, sometimes when you see the question, just by looking at the question, you can know which tool to apply. Okay, so it comes by practice and it comes by experience. That is the reason this combinatorics is very interesting field. Okay, even today a lot of research is going on. A lot of research. Actually, my own project was in combinatorics and graph theory in ISC. Okay, my MTech project was in this field. Anyway, so let's come back to this point. This is one more equation this you can find. Okay, and this equation is actually very easy to prove if you want. Okay, this is another equation. Okay, can anyone tell me how can you prove it? Actually, this is not hard to prove because you already know what is dn. See, derangement of n object. This anyone knows the formula for this? Basically dn. Okay, the formula you can like, even if you don't know the formula, you can very easily just check it out. The formula is very simple because what is dn? Dn is basically nothing but, okay, you have total n elements. Okay, just look at it. Okay, so 1 2 3 and so on, total n elements you have. Now what is dn? Dn is like this. Okay, so let me call, so like this. So what is dn? Dn means total permutations. Okay, so total minus undesired cases. Yes or no? Total minus undesired cases. What are the total cases? Total cases means total permutations. How many total permutations are there with the n elements? Can anyone tell me? How many total permutations? Total how many permutations are possible? N factorial. Total n factorial permutations are possible. Minus undesired cases. What are the undesired cases? Can anyone tell me what is the undesired case for derangement? Undesired case for derangement, that is at least one element in its own home. At least one element in its own home. Okay, and this is the area of inclusion exclusion principle. See, this is the area of inclusion exclusion principle tool. Yes or no? This is the area of inclusion exclusion principle tool. At least one element in its home. So let's find out at least one element in its home. How can we find out at least one element? At least one element, okay, in its home. So here we can very easily check it out. So here it will be, okay, like one element in its home, two elements. Okay, so it will be like this. Okay, one element in its home. So one element in its home minus two element in its home plus three element in its home. Yes or no? So for example, I can say that, okay, k element in its home. So that is, let me call it ak. Ak means basically when k elements are in their home. Okay. So you can notice this will be what? This will be A1, one element in its home, minus A2 plus A3 minus A4, something like this. Inclusion exclusion principle. Yes or no? So one element in its home. Can anyone tell me what is that? Like which element? So first of all, NC1. Which element you are choosing? Okay. So select one element. Now that should be in its home. The remaining element you can put them in n factorial, n minus 1 factorial base. Yes or no? See, this is a very simple point. I'm saying that, okay, this is n minus 1 factorial. Why? Because at least one element in its home means one element. So choose that element, NC1, choose that element and put that element in its home. So there is only one way. If I am putting you in your own home, then how many ways are there? Only one way. I can put you in your home. So that's only one way. For the remaining elements, and n minus 1 factorial base, because the remaining elements don't care. Okay, the remaining don't care. So you can notice minus two elements. Which two elements? Which two elements? Put them in their home, n minus 2 factorial plus nc3 n minus 3 factorial and so on and so on. Okay, so from this, what you got? This is actually what? So n into n minus 1 factorial. So this is just simply n factorial minus what is this? nc2 n minus 1 divided by 2 factorial. Okay, so this is n factorial by 2. If you notice, this is n factorial by 2. And this is what? This is n factorial by 3 factorial. So I can write like this. Minus this is n factorial by 4 factorial plus n factorial by 5 factorial and so on. Is this clear to everyone? So this is your undesired result. So I can say that dn is nothing but n factorial minus this undesired result. Okay, this undesired result means n factorial minus n factorial by 2 factorial plus n factorial by 3 factorial minus n factorial by 4 factorial and so on. Okay, so from here I can say that dn is nothing but n factorial minus n factorial. So that will just cancel out. Okay, so you can just, okay, this is inclusion exclusion principle. This is by inclusion there is something called inclusion exclusion principle. By inclusion exclusion principle. By inclusion exclusion principle. There is something called inclusion exclusion principle. So by that this happens. Okay, that basically this alternating like, okay, the proof of this inclusion exclusion principle, you can just check it out. This this type of situation happens. Okay, so actually it's very simple. At least one element in its home means, okay, one of them. Now here you have counted these cases. All these cases you have counted. Each of these cases actually you have counted 2 times. So we are subtracting 1 time and something like this. Okay, so you can just check it out. You can just read this inclusion exclusion principle. There it will be clear. Okay. So anyway, if you don't want, you can just remember this formula that we have derived. Okay. Anyway, this is the formula. So finally, what we are doing here. Okay. So what that will be? This will be n factorial. You can take out. Okay. And what you will get? So from here, what you can take? So this is cancelled and n factorial you can take out. Okay. So here you can say 1 minus 1 by 1 factorial plus 1 by 2 factorial minus 1 by 3 factorial plus 1 by 4 factorial and so on. So this is your final answer. Okay. Is this clear to everyone? Tell me. Is it clear? I hope this is clear. Even if it is not clear, you can just skip it. Okay. This proof you can skip if you don't want. Okay. Just skip the proof. But anyway, this is important. Okay. So finally, this result is important. Okay. So you can just remember this result. So this is your dn. Now from here you can very easily see what is dn minus 1. So now you can write dn in terms of dn minus 1. Okay, this won't be very hard. Okay, so because you already have dn. Okay, so here if you write this dn in terms of dn minus 1, you just then you will get this equation. You will get, you can check it out. Dn is equal to n dn minus 1 plus my so it's like, so this dn is basically n dn minus 1 plus minus 1 power n. Okay, because what is dn minus 1? You can just check it out. Dn minus 1 will be what? Can anyone tell me? N minus 1 factorial. Okay, n minus 1 factorial, and inside you will have 1 minus same 1 upon 1 upon 2 factorial and so. Now if you just check it out, if you put this value here, then you will get, okay, so like this. Anyway, these two equations you can finally, anyway, these are the two recurrence relation related to this derangement. Okay, so two recurrence relations related to derangement. One is dn is equal to n minus 1 dn minus 1 plus dn minus 2. This is one, and another is dn is equal to n into dn minus 1 plus minus 1 power n. Okay, so these are two equations. And the proof of this is very interesting. Okay, so this is interesting proof. This is boring. Okay, so anyway, the proof of this is very interesting. Okay, so anyone has any doubt right now at this point? Anyone has any doubt? Anyone, any doubt? Okay, so now let's see one more, that is division principle. And this division principle is also very nice actually. Okay, it is very important also, but most of the time you don't have to apply this. Okay, because the other tools that we have, okay, like permutation, combination, okay, all the other tools that we have, those tools you can apply, and most of the time, majority of the time, you will not have to apply this. Okay, but what is this division rule? Okay, so you can understand the division rule by this situation. So you can notice, to count the number of cows in a field, what you can do, you can count the number of legs and divide by 4. So this is the idea behind division rule. This is the idea behind division rule. Okay, so this is one example. Basically, if you want to count number of cows, what you can do, you can count number of legs and you can divide by 4. Yes or no? So something like that. Now you can let me just tell you what is this division principle. Okay, let me just, this division principle is actually very interesting. Okay, yes, this is the idea, like, okay, you can check. Okay, anyway, the formula. Okay, so this division principle is very helpful actually. Many times you will see this actually in the I think already in the Go classes I have taught this. Okay, and many examples I have taken for this. Yes or no, Sandeep, do you remember? So for this division principle, a lot of questions, a lot of proof I have given based on this. Okay, so this is very important. I told you. Okay, many questions you can solve based on this division principle very easily. Okay, many proofs you can do using division principle. Okay, so if you know this principle, then a lot of proofs. Okay, many things that you have by hearted, many things that you don't remember, like that you don't understand, those things you can very easily understand if you know this division principle. Okay, so anyway, let me tell you the idea of the division principle. So the division principle, before that, do you know what is a function? So what is a function? See, what is a function? Function from set A, for example, function from set A to set B. What is this? So this means basically every element in A is related to, is mapping to exactly one element in B, correct? So for example, this is your B. Now, for example, A, B, C, D. Okay, 1, 2, 3, 4, 5, 6. Now you can notice function means every element of A is mapping to exactly one element of B. Every element of A is mapping to exactly one element of B. So something like this. So this is a function. Okay, in function what happens? I can say that okay, exactly one element. Okay, for every element in A, there is exactly one image in B. So I can say that f of A that is equal to 1, and I can say that f of B is equal to 3, and I can say f of C is equal to 3. Okay, and I can say f D is equal to 6. So this is the idea of function. So this is the image of this one, is the image of A. Okay, and what is the pre-image of 3? Can anyone tell me what is the pre-image of 3? What is the pre-image of 3. Pre-image of 3 is basically b comma c. This is the pre-image of 3. Okay, means for this 3, this is the pre-image. And what is the pre-image of 2? Pre-image of 2 is basically 5. Okay, because this 2 is not related to, no one is mapping to 2, so that is the reason. Pre-image of 2 is basically empty set. Okay, so this is your function definition. Now, what is a k to 1 function? Now, let me tell you what is a k to 1 function. K to 1 function. So what is a k to 1 function? It basically means that, okay, this is a function. First of all, this is a function. So it means, because this is a function, so it means that every element is mapping to exactly one element. But actually k elements are mapping to, means every element here has k pre-images. So this is the k to 1 function. Okay, is this clear? K to 1 function means every element here has exactly k pre-images. So this is a function. Okay, and every element has k pre-images. Every element, whatever element you take, that has k pre-images. Every element, whatever element you take, it does not matter. So every element has basically k pre-images. Okay, this type of function I can say, okay, so I can say that this function f is basically k to 1 function. Remember, this should be a function. What it means, is it allowed? Tell me, is this a 2 to 1 function? Okay, for example, let me ask you, which is 2 to 1 function? Which is 2 to 1 function? First, let me give you this example. 1, 2, A, B, C, D. Is this 2 to 1 function? Is this 2 is this 2 to 1 function? Tell me. Which is 2 to 1 function? Which of them is 2 to 1 function? This is not even a function. So first of all, this is not even a function, because not even a function. Remember, this must be a function. 2 to 1 function. This is 2 to 1 function. This is not a 2 to 1 function. Why? Because I told you every element must have 2 pre-images. No, every element must have 2 pre-images. See, remember, k to 1 function means every element must have 2 okay, this basically I can say f from A to B is a k to 1 function. K to 1 function. Okay, k to 1 function. If and only if f is a function. If and only if f is a function, and every element, every x belonging to B, the cardinality of pre-image of x, that must be k. Okay, means every element, okay, every x belonging to B, for every element there must be k pre-images basically. Okay, what this means? This means every element, basically this means, okay, every element in B has exactly k pre-images. Okay, so this type of function is called k to 1 function. Now let's see what is the division principle. Now, okay, this division principle is basically just make a k to 1 function. If you have a k to 1 function, then can you find the cardinality? This is nothing. Okay, this is basically means okay, let's assume this is f is k to 1 function. Assume this is a d to 1 function. Okay, let's assume that this is d to 1 function. Then tell me, if this is d to 1 function, then can you tell me what is the cardinality of A? What is the cardinality of A? If this is a d to 1 function, then the cardinality of will be d into cardinality of B. And similarly, cardinality of D will be cardinality of A divided by D. Yes or no? Because this is a k to 1 function. So it means for k elements, you have one element here. Okay. For one element, you have k elements here. For one element, you have k elements here. For every element here, you have k elements here. For every element. Okay, so this is a k d to 1 function. This must be a function. Again, I am telling you. Okay. Sir, pre-images for all elements should be distinct. You tell me, Henry, if pre-images of two elements are not distinct, is it a function? Okay, in a function, can I say that pre-images of any two elements will be distinct, will be disjoint? Can I say that? Tell me, anyone? Pre-images must be disjoint, right? Else it won't be a function. Just think about it. Else it won't be a function. See, okay, in a function, okay, not question. So for example, if you have a function from A to B, okay, then and let x comma y belonging to B, then which is true? Tell me, then which is true? First, I am giving you pre-image of x intersection pre-image of y is definitely 5. Image of A tell me, this is correct, right? Because if just think about it, if two elements have, okay, if two elements share a pre-image, okay, like, okay, if this element has this pre-image, okay, and let's assume this element also has this pre-image, now this is not a function, right? This is not a function, correct? Okay, anyway, and does it make sense? Can anyone tell me this statement, does it make sense? First of all, this doesn't make sense. This doesn't make sense. Why? Can anyone tell me? This second statement doesn't make sense. Why? Because this is not a set. First of all, this is not a set. Image of any element is exactly one. Yes or no? This is also not a set. This is a set. This is a set. You already know this is a set. For example, what I want to say is this. Okay, if you have this function f from A to B, and let us assume this is A, B, C, and let us assume this is 1, 2, 3, then you can notice A, B, and this is function. So you can notice, for example, here you can notice what is the image of A. Image of A. Should I write this or should I write this? Which is correct? Which is correct? This is a function F. Which is correct? This is correct. This is not correct. Okay. So, but if I write pre-image, can anyone tell me what is the pre-image of 3? Should I write C or should I write C? Which is correct? Here this is correct. Here this is not correct because pre-image is a set. For example, what is the pre-image of 1? That is A comma B. Okay, anyway, so basically we were talking about this division principle, and this is very useful. Okay, so this division principle basically means that if you have D to 1 function, if you have this type of function, then you, okay, how can we apply this? This is the point, when to apply this. Okay, so actually division principle is also useful when you wish that, okay, some information was changed. Okay, so basically division principle is very useful in this situation. Just think about it. The division principle is useful when you ignore the unimportant differences, and if you find that question has become easy. Like, okay, if you think that, okay, if something was a little bit different, a small change makes your life beautiful, then you can use the division principle. So basically, use of division principle. When we can use division principle? Okay, if small change, okay, like, okay, this is just if small change in problem, if small change in problem makes your life easy, think about division principle. Think about division principle. Okay, think about this tool. As I told you, this is just a tool. So if small change in problem makes your life easy, then think about division principle. For example, consider this question. Okay, try this. Now, okay, before you try, okay, just try this question. Can anyone try? Just try whatever like whatever you do. Just think about it. Can you tell me which of them is easy? Okay, let me just change this word. See, just change this word. Okay, just change this word. Just change this word to different. To different. Now can you solve? Two different element means two different rooks. Now can you solve? If I change only this word, now can you solve? Just tell me. Can you solve now? See, now the question is very simple, right? Basically, you have an 8x8 chessboard. Okay, so this is your 8x8 chessboard. Okay, and so on. Now the question is saying that you have two rooks, two different rooks you have. Okay, so let's assume one is black, one is white. Okay, now you can notice that how many ways are there we can put them such that they are not in the same row or in the same column. In the chess game, you know, if rooks are in the same row, then they can basically kill each other. Okay, basically, okay, one of them will kill the other. Okay, anyway, so you can notice they should not be. So tell me, for this black, how many choices I have? Tell me, for this black, how many choices I have? Tell me. 64 choices. Yes or no? For this black, I have 64 choices. I can put it anywhere. For this black rook, I have 64 choices. Once I put it, once this work is done, how many choices for white? Anyone? Once this work is done, how many choices for example, let us assume black I am putting here. Now white cannot be put here, white cannot be put here. So how many choices for white? If black is there, then how many choices? 49. Yes or no? So total 49 choices. Total 49 choices, 7 into 7. So for this 7 into 7 choices, because now this is a 7 into 7 chessboard. Okay. Now this is just a 7 by 7 chessboard. Yes or no? This is just a 7 by 7 chessboard. Okay. So you can notice finally answer will be what? Okay. Answer is this. So answer is 64 multiplied by 49. This is your answer. Isn't it easy? So if you have different elephants, different rooks, then life is very easy. Very, very, very easy. Now the change is there, but both rooks are identical. Now what is the difference? Can anyone tell me? Can anyone tell me what is the difference? Now you can notice actually in this, if you notice in this, okay, when you have different rooks, when you have black, white, then actually these two situations are different. For example, you have black here, and let us assume you have white here. Now this situation is different from this situation. Okay, white and you have black here. So these two situations are now different. So when you have different rooks, so if you have different rooks, then these two situations are different because you have different rooks. Okay, but now in this, you can notice both these situations are same. Actually, in this, you can notice that, okay, this I can say this is rook. Okay, so this situation, because this is rook, okay, and this is same as this. Both are same actually. Can you notice? So this is the point here. Okay, so this is the difference here. Basically, here these two can arrange in two factorial ways. Okay, here these are, so now here you can apply the division principle, because you can notice that when rooks different, then your answer is what? When rooks different. When rooks are different, then your answer is 64 into 49. This is your answer. But what happens if your rooks are same? When rooks are same, then actually two cases are counted as one. These two cases will be counted as one. Yes or no? These two cases will be counted as 1. So it's like, okay, so it's like these two cases, okay, it's like these two cases will be counted as 1. These two cases will be counted as 1, and so on. So it's like this is a, I can say this is a K2 2 to 1 function. 2 to 1 function. Is this clear? So you have a 2 to 1 function. So simply divide by 2. Okay, so final answer will be, okay, so when identical roots, when you have identical roots, then answer will be simply, okay, then answer will be basically 64 into 49 divided by 2. Divided by 2. Is this clear to everyone? How to apply the division principle? So division principle is very simple. Okay, basically you can notice here, if this is different, then life is very easy. But because it is identical, so what you can do, you can find the different, what is the answer when it is different, what is the answer, and then you can see that two different are basically same. Okay, 2 to 1, 2 to 1. Can you try this gate exam? Okay, can you try this question? This is very simple. A is a set of students, this is set of tutorials, and there is a function, okay, and 12 students are assigned to every tutorial. Then according to division principle, this is the answer. Yes or no? This is very simple. Okay, so basically you have, it's like this. These are the students. These are the students, and these are the tutorials. Okay, so next, okay, now what is happening? 12 students are basically assigned to one tutorial. 12 students are assigned to one tutorial, like this. Okay, so here I can say that number of tutorials is basically number of students divided by 12. Okay, so here you can notice number of tutorials is equal to number of students divided by 12. This gate exam question, can you try? Using division principle, you can try this. Gate 1990. The number of ways in which 5 A's, 5 B's, 5 C's can be arranged. Can anyone tell me what is the answer? So actually you can apply this here also, you can apply the division principle. For example, if you have 5 A's, 5 B's, 5 A's, 4 B's, let's assume you have this. Then how many permutations? Then how many permutations? Here, how many permutations? Here you can notice that because they are same, if they are different, answer is, life is very easy. If they are the same, see, if they are different, here, just think about it. If they are different, A1, A2, A3, A4, A5, B1, B2, B3, B4. In this situation, what is the answer? Tell me. Can anyone tell me? If they are different, then life is very easy, right? Tell me what is the answer here. If this is the situation, then answer is 9 factorial. So in this situation, answer is very simple. Now you can notice that because they are same, so now you can apply the division principle. Just apply the division principle. Can anyone tell me what is this function? Can anyone tell me what is this? How much is this function? So you can notice that when all are different, then when all different, then answer is 9 factorial, because all are different. Okay, so because you can notice all are different, like, okay, A1, A2, and so on, like this. So because when all are different, now okay, now you have 5 A's and 4 B's, then tell me how, okay, what is this function? Can anyone tell me? Because you can notice one thing, very simple point you can notice here is that, see, if you change them among themselves, okay, for example, if you change this and this, no change will happen, yes or no? Here, from this point of view, from this point of view, from its point of view, if you change them, no change will happen. If you change them, no change will happen. If you change them, will any change happen? Tell me. If I change them, will any change happen? Yes. So you can notice here, if I change them, no change, no change. If I change them, no change. So can you notice that how many people here, basically they are same here? Can anyone tell me? Okay, let me take a small so that you can understand this. Okay, so for example, let's assume 3 A's and 2 B's. Let's assume this is your, okay, 3 A's and you have 2 B's. So you can notice this is 5 factorial. I am saying that, okay, so this is 5 factorial. But you can notice one thing, that actually all of them, they will map to this A1, A2, A3, B1, B2, A1, A3, A2, B2, B1, A3, A2, A1, B1, B2. Can you notice like this? All these basically they will map to 1 here, A, B, B. This is what I am saying. Yes or no? Actually, all of them, they are basically this. Yes or no? All of them will map to this. So tell me how many of them will map to 1 here? How many of them will map to 1 here? What is that? That will be 3 factorial into 2 factorial. Yes or no? Is this clear? 3 factorial into 2 factorial to 1. So these many people will map to actually. So 3 factorial into 2 factorial. These many people will map to 1. Is this clear? Anyone? Let me know. Anyone has any doubt in this? So this is why, okay, so now you can apply the division principle. So finally, the answer will be 5 factorial divided by 3 factorial, 2 factorial. Okay, like this you can find. Okay, anyway, this is just application of division principle. Okay, actually you can directly find, if you want, you can directly find answer. 5 A's, 5 B's, and 5 C's. So the answer will be nothing but total 15 factorial divided by 5 factorial, 5 factorial, 5 factorial. Okay, this is just a simple like, okay, another example you can take. For example, okay, school. How many permutations are there? Tell me. How many permutations? Here the number of permutations. Number of permutations. What is that? Number of permutations is 6 factorial divided by 2 factorial. This 2 factorial is coming because of this O. Because of this 2 factorial we are dividing. Why we are dividing by 2 factorial? Because if they are same, if they are different, just think about it. If they are different, if you have S, C, H, O1, O2, L, then the answer will be 6 factorial. There is no problem. Then the answer is 6 factorial. But because they are same, S, C, H, W, L, because they are same, so what is happening? 2 to 1 is happening. Yes or no? 2 to 1. Because for example, this O1, S, C, O2, H, L, O2, S, C, O1, H, L, these two will basically map to what? Can anyone tell me? These two will map to what? Can anyone tell me? These two will map to what? O, S, C, O, H, L. Yes or no? So that is the reason we are dividing by 2. Division principle. Okay. Very simple. Yes or no? Okay. Anyway, let's solve this question. This is GATE 1988. This we have done, right? This we have done. Can anyone see that in this question they are not considering empty string? Yes or no? In this question, you can automatically notice that they are not considering empty string. You can see. What is the answer for this question? The number of strings, binary strings, having n zeros, k ones. Having n zeros, k ones, which no ones are adjacent. See, when two people are never together, these are some templates I want to discuss. Okay, so this is a template when no two people are together. When a type of people are never together, a type of people, a type of elements are never together. In this template, what happens? What do you do in this template? When a type of elements are never together, then what you do? Arrange remaining elements. What you do? Arrange remaining elements and put this type of people in the in the spaces, in the gaps. Put this type of people in the gaps. Okay, so this is a template. This is template number 1. So can anyone try this? What is the answer here? So you can notice no two ones are adjacent. What it means? It means that just arrange zeros. So first you arrange zeros. Okay, how many ways to arrange zeros? Only one way. Yes or no? Because all are zeros. So just arrange zeros. Just arrange zeros. Okay, total n zeros you have. Only one way. Now, how many gaps? What are the number of gaps? Number of gaps. Number of gaps are n plus 1. Okay, this is this, and so on. So number of gaps is n plus 1. In these gaps, arrange ones. In these gaps, put k ones. So from these gaps, okay, total n plus 1 gaps are there. From these gaps, select k gaps. And in these gaps, you put ones. Okay, in these gaps, basically, you put ones, something like this. Okay, so here answer will be n plus 1 ck. So the answer is none of the above. Okay, sometimes you take care. Sometimes you take care. Make sure that these are not equal to this. Make sure that these are not equal to this. This is very important. Make sure that these are not equal to this. Okay. Here, okay, let me just tell you, okay, make sure before you put this, make sure that these are not equal to this. Okay. So like this. Anyway, this is your some factorial. You already know what is a factorial. N factorial basically means what? N into n minus 1 factorial. This is the recurrence relation for factorial. Okay, how to write recurrence relation for factorial? This is very easy because okay, like how to write recurrence relation. Okay, this is the this is the recurrence relation. You don't have to worry. If you want, you can check out the recurrence relation playlist on the Go Classes YouTube channel. Okay. Yes, set theory is coming. Okay, so you can notice this is n factorial is equal to this. And what is NPR? This is permutation. Basically, from n elements, permute r elements. What this means? From n elements, this basically means from n elements, permute r elements. This is the meaning. From n elements, permute r elements. Okay, and what this is? This is very simple. This is n factorial divided by n minus r factorial. Okay, the proof I have already told you the proof in the lectures. Okay, the proof of NPR. Okay, this we have already seen in the lectures, correct? And what is NCR? NCR is n factorial divided by n minus r factorial into r factorial. So the proof of this also we have seen in our lectures. So anyway, the proof is not needed now. Okay, because GATE exam is closing. Okay, GATE exam is coming. So you don't have to worry about proofs now. Okay, at this point of time, you should worry about the frequent concepts. Okay, variations, understanding. Okay, just understand the concepts. Okay, these basic proofs are not needed now. Okay, because these are very trivial proofs and we have already seen these proofs. Okay, anyway, so this is the point. Now, permutation combination, you already know. So let's solve some questions, some nice questions. Okay, the template, when some things must be together, then what should I do? This template one you have seen. What is another template? Another template is when one type of people are always together. What is this template? Are always together. Then what should you do? Tell me. Put them in a box. Put them in a box and treat as one element. Yes or no? Put in a box and treat as one element. This I told you. Because they must be always together. So what do you do? Put this type of people in a box. This is the template. Okay, so you can apply this template here. So here you can notice A, B, C, D, E, F, G, H and ABC containing substring ABC. Okay, so this substring must be there. So what you can do, this ABC you can put in one box. Okay, and this then you have D, E, F, G, H. So now you can arrange them. And so that is 6 factorial. Okay, So this is your 6 factorial. Like this you can do. Okay. Some important formulas you already know, I hope. NCR is equal to NC n minus R. Okay, because choosing n elements is same as choosing n minus R elements. So basically, I can say choosing R elements. Choosing R elements is automatically same as discarding n minus R elements. Yes or no? Both are same. Discarding n minus R elements. So if you are choosing R elements, automatically you are discarding n minus R elements. Okay, so this is the point. NCR means choosing R elements. So what is this NCR? NCR basically means from n, choose R. This is the NCR. Okay, so what is NCR? The formula is n factorial divided by n minus R factorial R factorial. Okay, so this is your NCR. In NCR, actually, one thing you should take care is, for example, okay, I will tell you after some time, but okay, after some time I will tell you. Anyway, this is binomial theorem. So binomial theorem is already clear to you. For example, x plus y power n. Okay, here actually, let me tell you, this is very useful. So let me tell you that this power can be anything. Okay, here, for example, let me tell you a few things. You know that if, can anyone tell me what is 4C? 5. What is this? 4C5 means choosing 5 elements from 4. Choosing 5 from 4. That is not possible, right? That is not possible. This means choosing 5 from 4. This means choosing 5 from 4. So this is not possible. So this is not possible. So this is not possible. So answer is 0. So basically 4C5 is equal to 0. 4C4, that you already know 1. 4C0, that is already 1. Because choosing 0 element, only one way, don't choose. Okay, choosing 0 element, how many ways are there? If you want to choose 0 element, choosing 0 element, how many ways? Choosing 0 element. It automatically means don't choose. So this is automatically a one way. Don't choose. So this is possible. Don't choose. This is possible, right? Not choosing is possible. Yes or no? So this itself is one way. Okay. Anyway, so you can notice that when n is integer, first of all, okay, when n is integer, or I can say when n is positive integer, or I can say, okay, so when n is basically positive integer. Okay, so at this point of time, when n is positive integer, then you can notice that nck, what is this equal to? This is equal to 0 when k is greater than equal to, when k is greater than n. If k is greater than n, then it will be 0. And if k is less than or equal to, okay, then it is, then you already know, then this is n factorial divided by n minus k factorial, k factorial. This you already know when n is positive integer. Okay. But in the generative function, you will see that in the generative function, this n can be any real number. Remember, this n can be any real number. It can be any real number. Okay. Then in that case, and k is a positive integer. This k is positive integer. In this situation, what is nck? In this situation, what is nck? So this, in this situation also, for example, what is minus 4c2? For example, what is minus half c3? Can anyone tell me what is the value of this? Can anyone tell me? Anyone? This is very useful in you can notice, okay, this is very useful in generative functions. This is very useful in generative functions. Extremely useful in generative functions. We will see. Okay. We will see tomorrow this. Okay. But so just wait for it. Okay. Tomorrow I will tell you. Okay. So this is very useful in the generative function. Tomorrow we will start with the generative function, and at that time I will tell you. Okay. So basically, what is this value? What is this value? Okay. Just wait for it. Okay. Tomorrow I will explain all these points. Okay. So right now you can just revise what is a binomial theorem. Okay. So this is your binomial theorem and some results you already know. So for example, nc0 plus nc1 and so on, ncn. This is equal to 2 power n. Okay. So this is your, where n is non-negative integer. And similarly, you can, okay, you can just check, okay, these are very famous results. Let's see this question. This is GATE 2019 question. Can anyone try this? In actually, this question is based on one story. Okay, in combinatorics, in basic combinatorics, three stories are very popular. Okay, so let me just tell you those three stories. All the enrolled students, they already know these stories. Okay, so let me tell you these three stories. These three stories are very popular and many times you will use these stories. So first story, or I can say story one or whatever. Okay, so what is the story? The story number one is basically, or I can say, okay, scenario number one. Okay, you can think like scenario number one. Okay, this story number one is related to Pascal identity. Pascal identity, and these are very important actually, because you can notice this GATE exam question, this type of GATE exam question are already present. Okay, this GATE exam question is not easy, but actually there are three stories I am going to tell you, and these three stories are, I can say, these are the basic. Like, okay, you don't have to worry about other stories. Of course, there are many. Okay, many are there. Okay, when you go to MTech, ISC, IIT, when you do MTech, okay, at that time you will see these things. Okay, so but right now let me tell you these three stories, and these are going to help you. Okay, and this question is actually based on our one of the story. Okay, so these three story I tell in every class. Already the enrolled student already know this thing. So what is the Pascal identity? So Pascal identity is like this. Anyone remembers? NCR is equal to, remember this is NCR. Okay, so for example, this NCR you can write like this also. NCR. You can write like this also. Okay, so these are different ways of writing NCR. Okay, so NCR is equal to what? NCR is equal to N minus 1 CR plus N minus 1 CR minus 1. Okay, this is called Pascal identity. This is called Pascal identity. And what is the story behind it? Behind this Pascal identity, what is the story? What is that? So the story is like this. You have total n people. Okay, so story for, I can say, Pascal identity. What is that? And these are important because many GATE questions are based on these three stories are very important. Okay, a lot of GATE questions you can solve. Okay, based on these three, because these are the basic. These are the basics. Okay, and I have already covered in the lectures. Okay, so all the enrolled students, they can find it in the lectures. Already it is covered. Okay, all these three. Okay, I think 4 or 5 stories I covered. So I think 5. I don't remember. You can tell me. Like, I think 5 something. Okay, anyway. So what is the story for Pascal identity? Very simple. You have total n students. So let's assume you have n students, and you want to select R students. This is what you want. You want to select R students. This is what you want to do. And let us assume in this class there is a particular student X. Okay, in this class, let us assume there is a student. Let us assume there is a student C. Okay, or I can say there is a student Y. Now you can notice. So there is a student Y. Now you can notice one thing. If you are selecting R student, how many ways are there? Can you tell me? Selecting R students, how many ways are there? NCR. Yes or no? I want to select R student from N student. How many ways are there? Total NCR. Now I can divide this in 2 cases. Y is selected, Y is not selected. Yes or no? Either Y will be selected or Y will not be selected. So tell me, if Y is selected, then how many ways? See, either Y will be selected or Y will not be selected. If Y is selected, then how many ways? You want R students, you have already selected Y. So from the remaining student, you want to select R minus 1. From the remaining, you want to select R minus 1. Now, you are not selecting Y. You are not selecting Y. So from the remaining students, you want to select R. This is the story behind Pascal identity. That's it. This is your Pascal identity, right? So Pascal identity has this story. So you have any student, you want to select R student. There is a student Y, either it is selected or it is not selected. If it is selected, then from the remaining student, you want to select R minus 1. If it is not selected, then from the remaining student, you want to select R student. So this is how you can remember this Pascal identity. Yes or no? Now you can extend this Pascal identity actually. Okay, you can take 2 students, extend. You can extend this Pascal identity. Yes or no? How can you extend? How can you extend? See, NCR, and okay, now select two students. Assume you have two students. So assume X comma Y, two students you take. Now what you take? You take two students. Now what are the cases? Either none of them is selected, X is not selected, Y is not selected, or or tell me, X is selected, Y is selected, or one of them is selected. X is not selected, okay, X is selected, Y is not selected, or X is not selected, Y is selected. So here you can notice that here from the n-2 student, you will select R student. Okay, here from n-2 student, you will select R-2 student. And here twice n-2 student, you will select R-1 student, R-1 student. Yes or no? Is this clear to everyone? So this is how you can extend the Pascal identity. This story you can extend. So this is another identity you can notice. Okay, this is so you can say that NCR is equal to n-1, okay, CR-2, okay, CR plus n-1, okay, CR-2, or plus n-2 CR-1 multiplied by 2. This must be multiplied by 2. Okay, is this clear? So like this you can do. Okay, so this is your Pascal identity. Another is Bonderman identity. Yes or no? Another is Bonderman identity. Or yeah, so here we have our story number 2. What is the story number 2? First of all, you look at this Bonderman identity. Okay, what this is saying? This is saying that you have n plus m people. You want to select R people, then that is equal to from n people you select R people, from n people you select k people, then from the remaining people you will select R minus k people, and this k is going from 0 to R. Yes or no? So anyway, this is this equation is known as Bonderman identity. Okay, Voldemort, whatever you, if you are a Harry Potter fan, you can call it Voldemort identity, whatever. Okay, so what is the story? How to remember this? So our story number 2, what is that? It's like this. See, whenever you see this type of situation, you should think about this story, n plus m. Okay, so this is your, okay, no, this is not Gandalf identity. Okay, so don't go to Lord of the Rings. Okay, I wish there was some Gandalf identity. I wish. Okay. Anyway, so anyway, so let's see this. Let's see this. So it's like this. Okay, let's assume there are total n women and total n men. N women are there and total m men are there. Okay, and from them you want to select R people. You want to select R people. Then how many ways are there? Can anyone tell me? You want to select R people. How many ways are there? From total n women are there, m men are there. You want to select R people. How many ways are there? How many ways? These many ways. Yes or no? Correct. So we have these many ways. Now you can notice that. Okay, so these many ways you have. Now you can notice that this same thing you can do like this. What you can do? You can say that. Okay, let's see how many men you are selecting. Okay, let's see how many women you are selecting. How many women you are selecting? See, you can select 0 women. Then how many men you have to select? Tell me. If you select 0 women, then how many men you have to select? R. Or if you select 1 woman, then how many men you have to select? These many, and so on and so on. If you select all the if you select R woman, then how many men? 0 men. Correct. So like this, that's it. So from here you can say that n plus m CR, this is basically equal to what? This is equal to summation. Okay, basically you are selecting k woman, and this k is going from 0 to R. You are selecting k woman, and you are selecting how many men? If you are selecting k woman, then how many men you are selecting? If you are selecting k woman, then how many men you are selecting? R minus k, yes or no? Because total we want R. Okay, yes or no? Is this clear to everyone? Is this clear? So this is your Voldemort identity. Okay, so this is your another story. This story is useful whenever you see this type of situation. You can use this story. And what is the third story? The third story, okay, this story number 3, this is like this. Okay, so it's like this. Let us assume you have total n people in a village. Okay, and from n people, basically you want to make a committee of k people. K people committee you want to make. K people you want to select. Basically you want to select k people, and these k people, one of them must be chairman. Okay, one of these must be chairman. One of them must be, one of them is chairman or monitor, whatever. How many ways are there? If I want to do this, how many ways are there? Basically, how many ways I have? So you can notice total n people. I want to select k people, and one of them I want to make monitor. So how many ways are there? So you can notice from n people you can select k people, and then from these k people you can select one people. Correct? Yes or no? So from n people you select k people, and then from these k people you select one people as a monitor. Okay, so this is your, I can also do like this. Select one person as monitor. First I select monitor. First I select monitor, NC1. First I select the monitor. So now monitor is done. Now what I need to do? First I select monitor. Now what I need to do? So monitor is already selected. Now I need to do, from the remaining I have to select k minus 1 people. Yes or no? From the remaining I have to select k minus 1 people. Okay, so we will see actually this story. Let's see how to use this story in. Okay, so sometimes this story is also very useful. Means you are making one of them monitor, making one of them chairman. Okay, so this story is also very useful. These 3 stories are very, very, very useful. Now let's see this GATE 2019 question. Okay, just by looking at this question, can you see which story they are applying? Just look at this question, which story they are applying. Look at the option number 2. They are applying something k. Okay, like, okay, let's see. Anyway, so let's solve this question. So first of all, the question is saying that you have a set U, okay, in which you have n elements. Okay, and you can notice, so this is your set U in which you have n elements, 1 2 3 and so on n. Okay, so this is your set U. Okay, now he is saying that let set A be one element and x. Okay, so it's like this, sorry, this is A, this has these type of things where you have this and you have this, means basically this x belonging to x. Okay, so it's like this. So you have a set, and from that set you are selecting one as a monitor. Yes or no? Isn't it? Can you think like this? Yes or no? There is a set, and from this set you are selecting one as monitor. So something like this. Okay, for example, this A has these type of things, 1 comma 1 comma 2 comma 3. These type of things A has 2 1 comma 1 comma 4 and so on. So this is your set A. Okay, now you can notice the question is asking the cardinality of A. How can we find cardinality of A? In these type of questions, story is very important. If you want to solve these type of questions in a snap of finger, if you don't want to waste time, okay, in a snap of finger, if you want to solve these questions, okay, then you can just, okay, just think about 2 ways. Basically there are 2 ways of thinking. Okay, just think in 2 ways. So very simple. See what is happening here. So first you can notice that there are 2 ways of thinking. What? First you make this and then you select one as monitor. Yes or no? This is one way of thinking. So what is the one way of thinking? Way 1. What is the one way of thinking? First you make this. First you select this. This is your first. Okay, so first you do this. First you do this. Then one of them you make as monitor. Yes or no? One of them you put here. Yes or no? Is it correct? So first you make X. Then one of them you put here. How can we do this? So to make this X, what we can do? This X can be any subset. Yes or no? And then from that we are selecting one of them. Or what you can do, see here. And another way, and way number two. So way two is first you select this. First you select this. So this you select first. First you select this, and then you make this. Okay, first you select this, then you include this here. And this is second. Yes or no? So these are the two ways of thinking. And these two ways of thinking are your option one, option two. Tell me, in this way of thinking, what is the answer? So first you select this element. How many ways to select this element? How many ways? Total n ways. You can select this element total n ways. Once this element is selected, then how many choices for this X? How many you can put here? See, once this is selected, once this is selected, once this is done, n ways are there. Once this is done, now how many ways? It is guaranteed that this X must be here. It is guaranteed. Anything else can be here or not. It is guaranteed that X must be here. It is guaranteed. The remaining elements may or may not be here. So the answer will be what? So here I can say that will be 2 power n minus 1 ways. So finally I can say using this way 2, I can say the answer is n multiplied by 2 power n minus 1. Yes or no? This is the cardinality of A, correct? Yes or no? Is this clear to everyone? Quite easy, right? Yes or no? So this is your option A. So this is done. This is your way two. This is your way two of thinking. Means first you select the monitor, then you make the committee. First you select your monitor, then you make the committee. And this is another way of thinking. First you make the committee, then you select the monitor. This is another way of thinking. What to do? First you select the committee and then you make the monitor. Now tell me, if you are making a committee, then what you can do? You can take k people, yes or no? Either I can make one people committee or two people or three people. So basically what I can do, I can make n k people committee. And this k is going from where to where? This k is going from where to where? 1 to n. Because at least one element must be there here. At least one element must be there because we need one monitor. We need one monitor. So that is the point. So what you can do? NCK. K is going from 1 to n. Now, once this is done, now how many ways here? K ways? Yes or no? Is this clear to everyone? Quite simple, right? I think like it is very simple if you think about it. And you can notice nothing, like very easily we are doing. So the answer is what? Answer is NCK multiplied by K. And this K is going from where to where? 1 to n. This K, how many people you are selecting? This K is going from 1 to n. And this is your option number 2. This is your option number 2. So the answer is what? So both are, this is also cardinality of A. This is also cardinality of A. So basically both are correct. Like this you can do. We did not use any, like we only using some story. Like way 1 of thinking, way 2 of thinking. You know, in Hindi there is a like anda pehle aayega murgi, anda pehle aaya hai murgi. So basically way 1 means anda pehle aaya murgi baad mein, and way 2 means murgi pehle aayi anda baad. Okay, is this clear? No, how many elements you are choosing? Like how many subsets of k elements can you tell me? How many elements, how many subsets of k elements can anyone tell me? If you have set S, if you have a set S and set S has cardinality n, then how many subsets of S of k elements? What is the answer? The answer is NCK. The answer is NCK. Why we are multiplying with K here? Can anyone tell me? Why we are multiplying with K? Because you are making the committee and then you are making the monitor. One of them must be monitor, right? See, you are making a committee of K people. You are making a committee of K people. One of them must be monitor, right? Yes or no? You must make one of them as monitor. Yes, this is KC1. This is KC1. Okay. So this is how you can do this question. Okay. In the GATE exam, multiple times this type of questions have come. Let me tell you, multiple times this type of questions have come. Anytime you see this type of question where same thing they are writing in two different ways. See, the same thing they are writing in two different ways. In this type of situation, you can always think about some story. Okay, and these three stories that I told you, these three stories are basically most popular. Most probably, one of these story will work. Okay, so if same thing they are writing in two different ways, okay, then just think about some story. Or like if you can think about some story, if you can, like with practice, actually, if you practice these type of things in our lectures, in our Go classes, discrete mathematics lecture, I think I have taken multiple questions. I think 4 or 5 stories. I don't remember, but multiple stories I have taken. And based on those stories, many questions, a lot of practice we have done. Okay. So like this, if you do a lot of practice, these type of questions, let me tell you, these type of questions will decide the toppers. Because these type of questions are very are not easy. Many students will not be able to do them, but if you practice enough, then you can do it in a snap of finger. It won't take more than 1 minute. Okay, this question will not take more than 1 minute. In this way too, see, first you are selecting a one monitor. Once you have selected this monitor, then how many superset you can make? This is the point. Ananya, is this clear? Basically, you are selecting one person, then here you are selecting set. So this X should belong here. So for the remaining, with the remaining elements, how many set you can make? With the remaining elements, how many subset you can make? 2 power n minus 1 subset you can make with the remaining n minus 1 elements. Okay. So like this. Okay. Now this is distribution of objects into boxes. So maybe we can complete this tomorrow. Okay. So distributing objects into boxes. Okay. So let me just take set theory. Okay. So this remaining portion of combinatorics. Okay. I will take tomorrow, but let me start set theory too. A little bit actually. Okay. Because set theory is actually comparatively very easy. Okay. So let me just take some set theory. Maybe we can take. Okay, so maybe we can start tomorrow. Okay. So let's leave it here. Okay. Tomorrow I am going to take basically this set theory questions also I have here. So you can just like, okay, pigeonhole principle, generative function. So actually I want to cover a lot of things. Okay. But anyway, so tomorrow we will take these questions, these set theory questions. Yes, group theory and all this. Group theory also we can start out. Please start at 5 p.m. Are you going to post soon? Yes, in the group I will post. Actually, tomorrow we will take the class on the YouTube. Okay. So on Go Classes YouTube channel, we will take the class. Okay. So you don't have to worry about the link. You can join from the YouTube. Okay. So actually, to all the enrolled student, I want to say that if you are already Go Classes student, then kindly go through your notes. Okay, because you can notice many of the things that we are because we are revising. All these things actually we have already seen. Okay, so in your notes all these points are present, and so you just revise them. Okay, those notes you definitely revise. Okay, so once you revise them, then these things will become very easy. Okay, so tomorrow what I'm going to do, basically I'm going to take questions actually. Okay, today some concepts I taught. Okay, but tomorrow I will try that concept I will only give overview. Okay, I will not give any proof. Okay, so we will just focus on the questions. Okay, because all the proof are already available on your notes. Okay, each and every proof is already I've already given to you. Okay, so at this point of time you don't have to worry about the proof. Okay, at this point of time you should worry about understanding. Okay, understand the question, completely analyze the question. Okay, thoroughly analyze. Okay, like what every option, everything. Okay, so like we have done today. Okay, so tomorrow we will take set theory, graph theory, group theory. Okay, these topics we will take, and we will try to cover as much as possible. Okay, as much as possible I will try to cover. Okay, so maybe we can start at 5 p.m. Okay, I will tell you. Okay, in the group I will mention. Maybe we can start at 5 p.m. so that we can cover more. Okay, I want to cover as much as possible. Okay. Any other doubt? Anyone? You can give me your feedback. Okay, you can send me a message on Telegram or WhatsApp. Okay, you can send me your message. You can give me some feedback like how can we improve the revision. Okay, because I don't want to waste your time. Okay, and you can notice from 6 p.m. onwards we are continuously studying. Okay, each and every minute, each and every second we have studied. Okay, so you just give me your suggestions. Okay, and how can we improve the revision course. Okay, like, okay. Yes, proof we will avoid. Okay, HP, we will avoid the proof. From tomorrow onwards, proofs will be avoided. Okay, and the Go classes students, they don't have to worry. Okay, because all the proof are already available in your notes. Okay, so from tomorrow onwards, there will be no proof. Okay, we will take questions and we will do a lot of variations and practice. Okay, this will come by practice. SK. See, all the things cannot be taught. Okay, some things come by practice. If you practice a lot, maybe 10-20 questions if you do, then you can very easily complete. Okay. Group theory, from group theory, very basic questions come. Okay, from group theory you don't have to worry actually. Okay, most of the time very fundamental questions they will ask from group theory, because group theory is a very big area. Okay, and very complicated area also. So as you can see from group theory in the GATE exam, very basic questions have come. Okay, there is no complicated question from group theory in GATE exam so far. Okay, so I don't think they will ask you any complicated question from group theory. Okay, complicated questions are asked from combinatorics. Okay, combinatorics, graph theory. Okay, so first order logic. So these are the areas from where they can ask you complicated questions. Okay, yes, Sandeep, we will see. Okay. Okay, thank you everyone. Bye, good night. You can send me message. Okay, if you have any suggestion, then you can send me message. Okay, thank you. Bye.